Last class we were discussing about potential due to electric dipole. So we were trying to derive the expression for electropotential due to electric dipole. So we have arrived till if you can recall, so it was up to the potential V is equal to 1 by 4 pi epsilon naught into 1 divided by r minus a cos theta minus 1 divided by r plus a cos theta. So we have derived up to this, and now in this class we will simplify this expression. So here it is q divided by, so q by 4 pi epsilon naught into, now let us take the common denominator. This will become r plus a cos theta minus r minus a cos theta divided by r minus a cos theta into r plus a cos theta. Take the common denominator. So we are finding out electric potential due to a dipole at some point r. So point r, so this is our dipole we took, plus q and minus q, and r is its distance from the center O. This is a, this is also a, so these are the distances. So now simplify this. So minus of minus plus a cos theta, and minus r plus r here will get cancelled. So we get V equal to q divided by 4 pi epsilon naught into a cos theta, minus of minus is plus, so this becomes 2a cos theta. Divided by, this is of the form a minus b, a plus b, a minus b into a plus b. So that is r square plus a square cos square theta, r square minus a square cos square theta. A minus b into a plus b is a square minus b square. And we know the magnitude of the dipole P, dipole moment. The magnitude of dipole moment P is q into 2a. So in the above equation, substitute q into 2a as P. So we can get V equal to P cos theta divided by 4 pi epsilon naught into r square minus a square cos square theta. V equal to P into cos theta divided by 4 pi epsilon naught into r square minus a square cos square theta. Now if r is very greater than a, we will take the case for r very greater than a. That is, if we are finding a electric potential at a point which is very greater than a, V equal to P cos theta divided by 4 pi epsilon naught into r square. So electric potential is P cos theta divided by 4 pi epsilon naught r square. So this is the simplified equation for electric potential due to an electric dipole, and for this is a special case where r is very greater than a. Otherwise you can use the above equation, but generally this is the case because dipole is two equal and opposite charges which are separated by a small distance. So it's generally small compared to compared to r. So this is the expression for the potential due to an electric dipole. So now with this, let us see how we can do this problem. What is the work done? In moving a test charge q through a distance of 1 centimeter along the equatorial axis of an electric dipole. What is the work done in moving a test charge q through a distance of 1 centimeter along the equatorial axis of an electric dipole? How we can do this? So when we consider a dipole, first we'll see what is equatorial line. You know, last class we have studied what is equatorial line of a dipole. Now if this is a dipole, say plus q and minus q, and if O is the center, equatorial line is the line which is passing through the center and perpendicular to the axial line of the dipole. So this line is the equatorial line. So equatorial line of a dipole is the line perpendicular to the axial line and passing through a point midway between the charges. I'll write here. Is the line passing through is the line perpendicular to the axial line and passing through a point midway between the charges. Now the question is to find out the work done in moving a test charge q through a distance 1 centimeter along the equatorial line. Now let us say we are considering 2 points A and B. We need to calculate what is the work done in moving charge q from B to A. So let me say the distance between A and B is 1 centimeter. Now the electric potential at any point on the equatorial line due to an electric dipole is equal to 0, because this line is at equidistance from charge plus q and minus q. So the potential due to plus q will be exactly same, but opposite in sign compared to the potential due to minus q, or the algebraic sum of potential of plus q and minus will get cancel each other because they are all equal distance from these points. Or we can directly apply the formula which we have learnt before. So I'll write a note here. The electric potential at any point on equatorial line due to an electric dipole is equal to 0. This you can apply the formula also. The formula says V is, just now we learned the formula for potential at any point V due to a dipole. So the potential at any point R due to dipole is given by V is P cos theta divided by 4 pi epsilon naught into R square. Now theta here is equal to 90 degree, or this side. So theta is 90 degree. You can refer the previous picture for what exactly is theta. Theta is 90 degree, so theta is 90 degree. That means cos 90 is 0. That is why we get the potential at any point on the equatorial line is 0. So because of this, no work is done in moving test charge along the equatorial line, or we can write work done in moving the test charge q from A to B is equal to q into VB minus VA, and both VB equal to 0, and because VB is a point on the equatorial line, VB is 0 and also VA is 0, and because of this the work done is 0. So no work is done in moving a test charge along the equatorial line of an electric dipole. No work is done in moving a test charge q along equatorial line. No work is done.